So this is a class of problems called projectile motion. And this is for things that are thrown, like that marker was. The projectiles are only influenced by gravity. And so we'll talk about that as we go a little bit. But it doesn't include things like rockets, which have propellant in them, and things like that. In chapter 1, we talked a little bit about conceptual models, and we create a conceptual model for this situation in which there's no air resistance. If things are going fast, air resistance is a big deal. But for our examples, we just neglect air resistance because it makes most of these, if you include them, it makes the math complicated enough that it's beyond the scope of the class. So we include no air resistance. We assume the Earth is flat. If you're a flat earther, that'll make you happy. We assume gravity is constant. Technically, as you rise up away from the Earth, gravity gets weaker. But since the distances we go up are small, a mile or something like that, compared to the size of the Earth, those are small. Gravity doesn't change much, and so we assume that it doesn't get any weaker for our purposes. We assume the Earth does not rotate. This also might make flat earthers happy, I don't know. We assume the projectile is only influenced by gravity. As I said, no motors, no propellant or anything like that. So airplanes don't count as projectiles. Rocks and balls that are thrown do. So, to that end, all statements refer to just after the projectile leaves whatever's throwing it or launching it to just before it hits. And so if I ask you the question on a homework or on a test, what's the speed of the projectile when it hits the ground? 0 is not considered a correct answer because it stops when it hits the ground. What I'm asking for when I say what is the speed when it hits the ground is how fast was it going just before it hit or just after it was thrown. So all statements refer to while it is still a projectile, while it's in the air. Okay, and so this is a class of problems that we're going to address at this point. So this is a demonstration of to show that projectile motion can be treated as independent horizontal motion and vertical motion. This is a little launcher here. So this is a cart that rolls, and it's got a little launcher that launches something vertically. So I'll show you that here. Right, so there's a little ball, and it's just going to get shot up into the air. Right, here's the ball. And a little launcher shoots it up into the air. So I'll do it one more time. And so what I'm going to show you is that I can take the cart and start it rolling, and then the ball's going to get launched straight up. But because the ball has the same motion as the cart horizontally, when the ball goes straight up and straight down, even though the cart keeps moving, so does the ball, it'll fall right back down the tube. Almost. Sometimes it takes 2 tries. One more time. So the motion of the ball and the motion of the cart horizontally are the same, right? But the ball is also moving vertically. And this demonstration shows that you can treat the motion of the ball horizontally just the same as the motion of the cart. They move in the exact same way horizontally. And that's what we're going to do with our math. We're going to let the motion of the horizontal motion of the ball be separated from its vertical motion. And then we can use the equations from chapter 2 where we wrote down equations for horizontal motion and then a separate set of equations for vertical motion, and those will allow us to solve for the motion of projectiles. So it turns out we'll be using a set of equations that you're already familiar with for projectile motion. So for a projectile, it's an object that's thrown, that lands, and so it's got some initial velocity v0, and then it travels some trajectory. You've all seen a football be kicked or a golf ball be hit or a ball be thrown or something like that, It follows some arc, and it lands. And we're going to separate its x motion, its motion in the horizontal direction, from its motion in the vertical direction. And I'll say more about that, and I'll show you an example or two. And so we've already got a set of equations for x motion. When we derived these, I didn't put x's on the velocities because we hadn't talked about vertical motion yet. So these were the 5 equations for horizontal motion of a projectile, and then we went ahead and said, look, if we have an object moving vertically, we had y equals y naught plus v average y times t. We had vy is equal to v naught y minus g times t. Remember, these are only influenced by gravity, so the acceleration in the y direction is just gravity, right? 3 was v average y is equal to vy plus v naught y divided by 2, and then we had 4 was y equals y naught plus v naught y times t minus 1/2 gt squared, and 5 was vy squared equals v naught y squared minus 2g y minus y naught. And we came up with these by just doing a switch to y variables and then change the acceleration to minus g. So when we're talking about projectiles, now we've got x motion for the projectiles because it's moving horizontally. We know vectors, we can treat them as horizontal motion combined with vertical motion, and that's what we're going to do. And so here are horizontal motion equations, and here are vertical motion equations, except there's one catch, and that's that the acceleration in the x direction is 0, because the only thing it's pushing on it is gravity, and so it can't accelerate in the x direction. And so the x side becomes a lot simpler. This part goes away because a is 0, a equals 0, and technically I can call those a sub x because they're acceleration in the x direction. But this becomes 0, and this piece becomes 0. And so these equations become a lot simpler. I just get vx equals v naught x, which basically just tells me that the x velocity is constant. That's the final velocity equals the initial velocity. This says the same thing. Since these two are the same, then the average of them is the same. And so this equation is unnecessary because it's the same as this one, right? Similarly, this is just vx, x equals x naught plus v naught x times t, but vx naught x is the same thing as the average x, and so this equation is the same as that equation, so I can kill that one. And this just says is vx equals v naught x, since this piece is 0. If these two are equal, their squares are equal, and so that's unnecessary. And so all of my x equations for projectile motion are right there, and if you wanted to, you could add this. And so for projectiles, these are my equations of motion. This is what's happening in the x direction, and this is what's happening in the y direction. And so we already looked at particles that are just moving under the influence of, in vertical motion under the influence of gravity, right? And now we're also allowing them to travel in the horizontal direction. And so we're going to combine these two equations and watch what the projectiles do. We can determine their position and so on by using the two equations at the same time. Okay, this is a cart, and it's got a little springy ball in there. So it shoots the ball out, just like I showed you. try to catch it this time. You can see that, hopefully. And so what I want to show you is that the vertical motion and the horizontal motion are independent. I'm going to pull the cart forward so that it's rolling. The ball is inside, and the ball is going to roll with the cart. And then I'm going to yank the string out, and the ball is going to go as a projectile, and it's going to land back in the pipe. The pipe's going to move horizontally, while the ball follows an arc, and they'll get to the same spot at the same time. All right, this may take a few tries. So I'm going to drag the cart horizontally and pull the pin, and that's going to launch the ball up, and the ball will follow an arc, and the cart will just move horizontally, and they'll get back to the same place at the same time. The horizontal motion is independent of the vertical motion. The ball just goes straight up and straight down, like that, if it doesn't bounce back out. All right, I'll try to keep it in there. Well, it lands back in the spot, it just won't stay in there once it lands. And so, I'm going to put it back in here, and I'm going to launch it. Try this ball. All right. So this is this is just a spring-loaded cart. It shoots a ball up in the air like that. And so I'm going to take the cart and I'm going to pull it across, and the cart's going to move horizontally. It's going to launch the ball vertically. The ball will follow an arc because it's got the same horizontal motion as the cart, because they're moving together when it gets launched. And so when it goes back up, it comes back down, and it'll go right back into the same spot, showing that the horizontal motion and the vertical motion could be treated independently. That is, the horizontal motion of the ball is exactly the same as the horizontal motion of the cart. And so when I combine the horizontal motion of the cart with the vertical motion of the ball, that gives the trajectory of the ball. Because the horizontal motion of the cart and the horizontal motion of the ball are the same. Ta-da! So in this demonstration, I have a ring and a ball, and I'm going to flip this little lever, and it's going to shoot the ball this way and drop the ring straight down. And hopefully you'll be able to see that the ring and the ball hit the ground at the same time. What we're trying to show here is that the horizontal motion for the ball is independent of its vertical motion. That is to say, the ring and the ball will hit the table at the same time, even though the ball was initially moving horizontally and the ring was initially moving straight down. So let's see how this works. Hopefully, if you could see those, you saw that they hit the ground at the same time, hit the table at the same time. So this is a demonstration of what do you want?
Well, I just wonder what you want me to do. You're strumming.
I was going that way, but it doesn't matter.